Hey everybody. So I got several messages, and I noticed it also showed up on the discussion board a question about a couple of problems in section 11.2, or sorry, I'm so used to using the Stewart book, I always refer to things by those sections, and I know some of you aren't. So the section on series, in particular, the geometric series. So I wanted to make a little video about it since it seems like it came up in office hours, as well as emails, messages, and discussion board. And while we're at it, I'm going to plug using the discussion board again. Over the weekend, I know people have been sending messages since yesterday, but I haven't really been looking until this morning. So you're likely to get help from somebody else if you post there before I get a chance to do it. Anyways, so I've written here two formulas for the geometric series. Because I just wanted to note that when we're dealing with these sums and these series, that indexing, meaning how we number the things, can change how we write things down, but the meaning is the same. So I have two different formulas here, and I just wanted to quickly make sure that everyone sees they're exactly the same thing. So in the first case, where I have n equals 0 to infinity, a r to the n, just going to write out the first few terms. When n equals 0, I get a times r to the 0, so just a. So I'm starting at 0, and then when n equals 1, I get plus ar squared, and on and on and on. When I start my indexing at 1, but I write the formula as ar to the n minus 1, the exact same thing happens. Now I start at 1, I get a times r to the 1 minus 1, or to the 0, I get a. Then when n equals 2, I get 2 minus 1, so I get AR, and on and on and on. And so even though they look a little bit different, they're spitting out the exact same series, okay? And it's personal preference. I tend to start at 0 if there's no good reason not to, but I certainly start at 1 sometimes just for whatever reason. It's not really important. What's important is we know what we're doing and what the index is doing. And when you're looking at other materials, so maybe you've looked up videos online or other resources, they may use indexing that's a little bit different. And this will always come up, that we might write things down a little bit differently, but the meaning's the same. In any event, in both cases, when we're given a series that's a geometric series, or we think is a geometric series, we want to write it down in whichever format we like. I'm gonna use this first one today. And figure out what's playing the role of A, what's playing the role of R, what's playing the role of, and we know what N is. So with that in mind, let's go ahead and take a look at the first question. So I believe this is question 5. Yours might look a little bit different. I've got it here on the side. I'm going to rewrite it so we can see it a little easier. Your numbers might be a little bit different, but the process should be the same. Minus, oh, that's got a plus minus. I think I didn't write this question. Oops, whoever didn't quite format it perfectly, but I think we'll be all right. Minus 2 over 227 plus 2 over 81, and on and on and on. Okay, so if I suspect this is a geometric series, first I need to know that it is, and then I need to know what is A and what is R. So a geometric series just means that each term, to get from one term to the next, we are always multiplying by the same constant, okay? So I'm just gonna write that down, just see what happens, right? How would I get from negative 2/3 to 2/9? Well, I would multiply by negative 1/3. Then to get from 2/9 to 2/27, I would multiply by negative 1/3 again, and to get from negative 2/27 to positive 2/81, I would multiply by negative 1/3, right? So this is a geometric series. Our ratio, our common ratio, is negative 1/3, which means if I want to, I can write this series out with our summation notation. A is going to be the first term and then the common ratio is -1/3 to the n. And right, it's always good to double check we did things right. Let's just plug in values for n right out the first few terms. When n is 0, this term is a constant, is the constant 1, so we get our -2/3. Then when n is 1, we get -2/3 times -1/3. That gives us +2/9. And when n is 2, we get that, and so on and so forth, right? So if you plug in the values of n and go through, you should, to double check, you can see that we've got the right thing. And so with that in mind, now we know that we can use this formula. Remember, this formula works as long as the ratio is less than 1 in absolute value. So between -1 and 1, this series will converge, otherwise it diverges. So this one, our common ratio is -1/3, which is certainly less than 1 in absolute value, or between -1 and 1. So that means the sum of this series is given by A, which we just said is -2/3, over 1 minus R, which is -1/3. And then we just have to do the algebra to work this out, which is going to be -2/3 times 4/3, which gives us, what is that? Oops, I wrote that wrong. That's not correct. I forgot to flip that. Times 3/4, excuse me. And so we get, cancel our 3's, cancel this, cancel that. We get a -1/2. So this sum that was given sums to, I wrote 1/3, sorry, I'm being a little careless here, -1/2. Right, this sum sums to 1/2, which means, remember, that the sum, as we take more and more terms, gets closer and closer to 1/2, right? And we can get it as close, -1/2. We can get it as close as we want to -1/2 by taking n to be large enough, or the limit of partial sums is -1/2, right? That's really how we define the sums of these infinite series. Okay, so that was that problem, right? So yours is going to have different numbers, but the process should be exactly the same. I would plug it in, but this is just a screenshot of the problem, so it won't respond to anything I do to it. All right, let's take a look at the other one that I got several messages about. That one, most people were just, the messages I got, people were a little confused about the notation here. So let me write it again. It's on the side here, but we're given this expression, a sub n is equal 40 over 40 to the n. Again, the question is, the question might look a little different for you. The numbers might look a little different, but the process will be the same. Okay, so the first part asks you, and then it gives you two cases and asks you if the expression given is convergent or divergent, and if it converges, find the limit of the convergence. Okay, so this is really a question about notation and understanding the meaning of certain things. So the part that people seem to actually get the second part correct. The first part seemed to be causing more problems, where they wrote this expression. Okay, and we have to know what they mean by this. This is, and actually I'll just compare it to the other expression. The other expression given was this one. And so most people recognized that the second expression, they were saying, oh, let's check on the convergence of this series, right? Does it add up to anything? This expression, the first one with the brackets, is the sequence. In other words, this is the sequence. We'll start at 1, just like they did on the series. It actually doesn't really change anything about the convergence, but this would be the sequence: 40 over 4 to the 1, 40 over 4 squared, 40 over 4 cubed, 40 over 4 to the 4th, and on and on and on, right? It's a list of numbers, okay? So a series, remember, adds those numbers up, but the sequence is just a list of numbers. And so all we're asking here is, does this list of numbers approach something? Not adding them up, just do the individual numbers. And we have a rule about this. We can treat these sequences, we can look at the functions that have the same values on the integers, right? A sequence is really just a function whose domain is the integers, right? We write it differently because we kind of do different things with them, so we like to think of them a little differently. But this is just a function whose at input 1, the output is 40 over 4. At input 2, the output is 40 over 4 squared. At input 3, the output is 40 over 4 cubed, and so on, right? So what we do, I'll do a little work off to the side. We think of a function, f of x, that if I put in any integer, it has the same value. So in other words, if n are the integers, this function f spits out the same terms as our sequence. And then we have this rule that the limit as x goes to infinity of f of x is the same as the limit as n goes to infinity of a sub n, okay? So that's technically how we solve these problems. We find a function with the same values as the sequence on the integers, and then take the limit of that function, and then we just use all the stuff you know about limits from previous calculus courses, right? Now, in practice, we usually get a little bit lazy and just write out this, right? The limit as n goes to infinity of 40 over 4n. There's nothing really wrong with this, but it's technically, we're skipping over that we should be kind of going by way of a function and then using this property over here once we take the limit as x goes to infinity of our function. But we're kind of just short stepping this because we know it looks exactly the same. It's just changing out n for x really in practice. So in this case, when we look at this, we can, if we want to, constant slip out of the limits. And then we have 1 over an exponential. And at some point in Calc 1, we should have learned that this is something that's going to go to 0, right? An exponential in the denominator grows without bound, so we can make that fraction as small as is conceivable without ever reaching 0, but we can get as close to 0 as possible. And so this limit is 0, okay? Okay, so that's that one. Let's finish the other part just for completeness. Notice, now we know that this has a chance of convergence. We haven't proved that it converges, but we know that for it to converge, it must be the case that the limit of the sequence of terms is 0. If this limit of the sequence is 0, it doesn't mean it has to converge, but if it's not 0, it can't converge. So now we know at least that this has the possibility of converging. So I want to do a little bit of work here. So there's our terms. This looks like it's a geometric sequence as well. Let's see if we can write it that way. So I'm just going to do a little bit of manipulation here. I'm going to pull out 40 over 4, which leaves n minus 1 factors of 4, right? So that's just algebra right there. That's all I've done. Like, it's confusing because we've got this summation in front of it, but all I'm doing is thinking about this part right now. And these are just numbers that I can manipulate just like I can in algebra. So convince yourself this is exactly the same as the thing above. We just multiply fractions across. And when we multiply 4 times 4 to the n minus 1, we add exponents. This 4, of course, has a little 1 there. So that works out the same. And we'll see in this step why I did it. 40 over 4 is just going to be 10. And then I've got, I'm going to use properties of exponents to rewrite this way. 10 times 1/4 to the n minus 1, right? So I did this because, remember what we talked about last time, they started their indexing at 1, and so this is the form of the geometric series, right? There's this summation form I wrote on the last page. that looks like this, right? So this is just the indexing at 1 with n minus 1. So they started their indexing at 1, so I wanted to write it in this way with the exponent n minus 1. That's why I peeled off that 4. I could have done it alternatively, where I had changed the indexing to 0. I wanted to do one example this way. So now we recognize this is a geometric series. Its ratio is less than 1 in absolute value, and so we can apply our formula. So just looking at this, a is 10, and we have 1 minus 1/4, which gives me 10 over 3/4, which gives me 10 times 4/3, which gives me 40/3. Sorry that I don't like stringing them along horizontally, but I was running out of room here. So there's our 40/3, which you can see is this particular student had put in and got correct, just to confirm. So that's it for this. Again, I got several questions on this, so I'm happy to see at least one person posted it to the discussion board as well. You're always welcome to send me questions, but you're better off, unless it's something that's personal and you don't want to share with the class, I'm going to just copy the questions to the discussion board anyway. I'll leave your name off if you message me, so that everyone can benefit from my response. I don't want to type the same response out to 12 different people who are emailing me. Instead, we can help each other out on the discussion board. Okay, that's it. Thanks, everybody. I will see you next time.